Hello, this is Modumath 3.5. The subject is dividing decimal fractions. Modumath text 3.5 goes with the tape. Open to this text now. Keep pencil and paper handy to solve problems and take notes. If you have any questions about the material or the machine, ask someone to help you. Let's start right in with an example. 9.468 divided by 15 hundredths, 0.15. The divisor is a decimal, and the first thing to notice is that mathematicians never divide by decimals. If the divisor is a decimal, they change it to a whole number. Here's how they go about it. You know that one way to write a division problem is like a fraction. It's a somewhat strange fraction because both numerator and denominator are decimals, but we can live with that. And you know that we can multiply numerator and denominator of a fraction by any non-zero number. The value of the fraction remains the same. Any non-zero number gives us quite a lot to choose from. We narrow it down by reminding ourselves of why we're doing all this. We want to change the denominator to a whole number. In this case, the denominator is 0.15, and we want to move the decimal point 2 places to the right. But as you may remember, this happens almost automatically if we multiply by 100. To multiply by 100, all we do is move the decimal point 2 places to the right. The decimal, 0.15, is changed to the whole number, 15. So far, so good. But if we multiply the denominator of the fraction by 100, we must also multiply the numerator by 100. Okay, we swing that decimal point 2 places to the right also. The division problem is now 946.8 divided by 15. And we achieved our goal. The divisor is, in fact, a whole number. Usually, we don't bother writing all this out. We write the problem in the usual division form. Looking at the divisor, we change it to a whole number by moving the decimal point as many places to the right as necessary. But we keep track of how many, and the very next step is to move the decimal point of the dividend, that was the numerator when we wrote it the other way, the same number of places in the same direction, to the right. Like two dancers in a chorus line, they move the same amount in the same direction. Actually, we're not working with the original division problem anymore. We've replaced it by a new one. But we don't mind. All we really care about is the answer, and we know the answer will be the same. Here are a few to try yourself. You'll find them in your Modumath text labeled Figure 1. Don't worry about the actual division. Just set up the problem and change the divisor to a whole number. We'll write out the first one to give you the idea. Do the rest now. Compare your answers with these. We did the first one. The divisor had one decimal place, so in the division problem, we moved both decimal points 1 place. The second divisor had 3 decimal places, so we moved both decimal points 3 places. The third problem works the same with 2 decimal places. If you had any trouble with these problems, replay the tape or ask someone to help you. Otherwise, you're ready to go on. There is one small difficulty. It's illustrated in this example. 173.2 divided by 0.653. We change the divisor, 0.653, to a whole number by moving the decimal point 3 places. But the dividend, 173.2, has only 1 decimal place. When we try to move the decimal point 3 places to the right, we find ourselves going off in space. But we can handle it. Just remember, the idea behind moving the decimal point is multiplying by some power of 10. In this case, it's 10 to the 3rd power, or 1,000. Well, what happens if we multiply 173.2 by 1,000? We get 173,200. The decimal point in the division problem is right where it ought to be. All we need do is fill in the empty spaces with zeros. Of course, if the divisor is a whole number to begin with, you don't have to worry about moving the decimal point. Before we continue, let's review. The first step in dividing decimals is to make sure the divisor is a whole number, not the dividend. We're not worrying about the dividend, just the divisor. We get this done by thinking of the problem in this form, like a fraction, and multiplying numerator and denominator by the right power of 10. This is the idea. But in practice, we use the shortcut shown. If the decimal point is off somewhere by itself, fill in the gaps with zeros. With that much behind us, we're ready to divide. Question 1 is, where do we put the decimal point of the answer, the quotient? Well, it works the same as dividing whole numbers. The decimal places of the quotient always line up with those of the dividend. Hundreds over hundreds, tens over tens, units over units. That goes for decimal points too. So the next step is to write in the decimal point of the answer, directly over the decimal point of the dividend. And now, before we do any dividing at all, we're going to check out 4 different things that could happen in dividing decimals. The first possibility is that the division comes out even, just as it stands. No remainder. Here's an example. And we're going to keep the example simple so we don't get bogged down in the numbers. 0.852 divided by 0.12. Turn 0.12 into a whole number by moving the decimal point 2 places to the right. Do the same to the dividend. Write the decimal point in the quotient and divide. We work just as we would with whole numbers, even though there's a decimal point in the answer. The answer is 7.1. That's the simplest case. The second possibility is shown in this example. 1.15 divided by 0.4. Move the decimal points. The problem becomes 11.5 divided by 4. Write the decimal point in the quotient and start dividing. The quotient begins with a 2, decimal point 8, and now we have to pause. We've used up the digits of the dividend, We have our quotient with 1 decimal place, and there's a remainder of 3. But we can, if we like, carry this problem further. You remember that writing zeros after the last digit to the right of a decimal point doesn't change the value of the number. We can write as many as we please. If we put in a couple, we can continue the division problem further and get a more accurate answer. We bring down the first 0. The next digit in the quotient is 7. And there's a remainder of 2. Our quotient so far is 2.87. If we wanted it accurate to only 1 decimal place, we could round off to 2.9 and call it quits. But let's see what happens if we bring down 1 more 0. The 2 becomes 20. 4 into 20 goes 5 times. And now the remainder is 0. We're done. Not in the sense that the answer is close enough for our purposes, but in the sense that it couldn't be any closer. It's exact. The quotient is exactly 2.875. In the first case, 0.852 divided by 0.12, we got the exact answer without writing in any extra zeros. In the second case, 1.15 divided by 0.4, we got an exact answer by writing in 2 extra zeros. Now, 2 zeros is a reasonable number, so we'll describe this possibility as follows. It's the case where you get an exact answer by writing in a reasonable number of zeros. What's reasonable? Oh, say 5 or less. But suppose we wanted the answer accurate to only 1 decimal place. We never would have carried the work this far. We would have stopped right here and rounded off to 2.9. So we never even would have known that it could come out even. What's more, we wouldn't care. We'd have an answer that was accurate enough for our purposes, and that would be enough. In other words, the question of whether a division problem like this might come out even sooner or later is less important than it appears. The important thing is to get a quotient that's accurate enough to do the job we want it to do. And this takes us to the third possibility, problems where the answer comes out even if you plug away at it long enough. But why should you? Here, for example, is 7.34 divided by 12.8. Move decimal points, place decimal point in quotient, and start dividing. Here we write in some zeros, bring down one of them, and another, and another, and isn't it time we stopped? What are you going to do with this answer that you needed so accurate? Shoot yourself off to Mars? For practical purposes, extra accuracy is very expensive. More expensive tools, more expensive measuring instruments, more parts to throw out. You wouldn't bother unless you really needed it. In this case, we're perfectly happy with the decimal places we already have. We take a minute to round off the answer, and then we stop. Now, mathematicians have ways to show that this problem, continued long enough, will in fact come out exact, that is, with a remainder of 0. But we couldn't care less. The big question in our minds is not, how can I get an exact answer, but how close do I want it? In the fourth possibility, how close is the only question we can ask, because in this case the answer will never come out exact. Here's an example. 2.4 divided by 11. The divisor 11 is already a whole number. Locate the decimal point in the answer and start right in to divide. The quotient is decimal point 2, 1, 8, 1, 8, 1, 8, and we soon see that no matter how long we continue, we'll keep getting these digits alternately. 1, 8, 1, 8, 1, 8, 1, 8, 1, and so on. Sometimes we write it this way. The line over the 1, 8 tells us that part repeats indefinitely. In this problem, the quotient will never be exact. We never get a remainder of 0. We must start by deciding the answer should be accurate to 1 decimal place, or 2, or 10, or 100, or whatever you like. Once you've achieved that accuracy, you're done. You can't wait for a remainder of 0 because you'll never get it. By the way, in this example, the digits formed a pattern. 1, 8, 1, 8, 1, 8, and so on. If you can't get an exact answer, you always get a pattern of digits, as you did here. Such decimals are called repeating decimals, because sooner or later you get a pattern that repeats. The decimals that do come out exact sooner or later are called terminating decimals. To terminate means to end. A lot is known about the patterns of repeating decimals, how long they'll be and when and why we get them, but we won't go into all that now. The important thing for our purpose is, when the quotient is a repeating decimal, we must decide in advance how accurate we want the answer to be, because that's the only way to know when we're done. But actually, this is the important question for every division problem with decimals, whether the quotient terminates or not. Remember, when you begin a problem, you don't even know if it terminates, so it doesn't make sense to set that as your goal. If it terminates right away or in a step or two, you'll find out. If it terminates after more steps, say 5 or 6, you may find out and you may not. But what's the difference? Suppose it terminates after 80 or 100 steps. Chances are you'd rather not find out. Of course, the answer may turn out to be a repeating decimal. In that case, you can round it off, or you can write the repeat with a bar, as shown. By the way, one extra word is needed about rounding off. If you want the answer accurate to 1 decimal place, you must compute 2 decimal places, so you know how to round off. Similarly, if you want 2 decimal places, you must carry out the work to 3 for the same reason. However many decimal places you want, if rounding off is required, you must figure out 1 more and then round off the quotient. We'll use this in the next problem. Here we're asked to divide 7 by 3, accurate to 2 decimal places. Except for the last part, accurate to 2 decimal places, this wouldn't be a problem in decimals at all. It would simply be 7 divided by 3, which is 2 1/3. But that extra instruction about the decimal places means we can't leave the answer in this form. We put a decimal point after the 7 and write in zeros. It doesn't really matter if we have extra zeros, they can't hurt, and we use only as many as we need. We start the problem in the usual way. Place the decimal point and start dividing. 3 goes into 7 twice. 2 times 3 is 6. Subtract. Remainder of 1. And now we bring down the first 0. 3 into 10 goes 3 times. 3 times 3 is 9. Subtract. Remainder of 1. Bring down another 0. Repeat the process. 1 more 0. By now you may recognize that you're into the repeating pattern. It's nothing more than a whole string of threes. We were asked to give the answer correct to 2 decimal places. So it's 2.33. In the next tape, you'll learn about changing fractions to decimals, and you'll find yourself doing this kind of job all the time. One more detail. When we learned to multiply decimals, we saw that to multiply by 10, just move the decimal point 1 place to the right. To multiply by 100, move it 2 places to the right, and so on. To divide by these numbers, as you may have guessed, we do just the opposite. To divide by 10, move the decimal point 1 place to the left. To divide by 100, move it 2 places to the left. 1,000, 3 places to the left. You get the idea. This will save a lot of time when we come to percents. In that material, we divide by 100 pretty often. Meanwhile, let's review the important ideas of this tape. In any division problem involving decimals, the first step is to make sure the quotient is a whole number. We achieve this by moving the decimal point as many places as necessary to the right. Of course, we move the decimal point of the dividend the same number of places to the right. Next, we place the decimal point of the answer directly over the decimal point of the dividend. We saw that when we divide with decimals, the quotient may sooner or later come out exact, or it may never come out exact. It may form a pattern instead. If it comes out exact, either right away or after we add some zeros, we call it a terminating decimal. Otherwise, we call it a repeating decimal. When we start the problem, we don't even know whether the answer will be terminating or repeating, so there's no sense worrying about it. A more sensible approach is to decide in advance how many decimal places we need and carry out the division only as far as we have to. Finally, we saw a shortcut for dividing by 10, 100, 1,000, and so on. If you had any difficulty with the ideas of this tape, replay the tape or ask someone to help you. Otherwise, you're ready to try the problems in your Modumath text.